We are going to start with something new this morning. So far what we have seen is that using a simplified shell momentum balance, it is possible to account for all the forces acting on the different surfaces of the shell, and we can calculate, we can express the convective momentum that comes into the system, the conductive momentum, in other words the molecular transport of momentum, or the shear stress which is acting on the lateral surfaces of the control volume. And we have also identified that the forces which can act on such a control volume would be the surface forces and body forces. And in our examples so far, we have used pressure force as the only surface force and gravity as the body force. If the system is at steady state, then we understand that the sum total of all these, that is rate of momentum in by two different mechanisms minus rate of momentum out plus sum of all forces acting on the system, must be 0 in order to maintain the steady state. So, this gave us a difference equation. This difference equation, where the smaller dimension is allowed to approach 0. In other words, we have used the definition of the first derivative when let us say del x tends to 0. The definition of the first derivative would give rise to a differential equation. So, that differential equation explains or describes the motion, the laminar flow, the laminar motion of fluid layers slipping past one another. It is at steady state and there are no unbalanced forces acting on the system. Many of our everyday examples are at steady state, and it is possible to use the shell momentum balance to obtain concrete expressions for velocity for such systems. We have used the case of flow through a pipe, flow through a tube, and we have seen how the velocity varies as a function of radius. All these cases that we have analyzed are one dimensional flow. So, for example, in the case of flow through a tube, on the application of a pressure difference and gravity, it was a vertical tube. The velocity was a function of radius, but it was not a function of the actual distance, which is z. So, velocity over here at a fixed r location and velocity at some other value of z at the same r location, these two velocities are same. So, the velocity does not vary axially, it only varies radially. And we have also found out that the velocity distribution was parabolic in nature with the maximum at the center line, and from the expression of the velocity, this is differential approach, where we get the parameter of interest, in this case velocity, at every point in the flow domain. And from this velocity profile, we could differentiate this velocity profile, and if this is a Newtonian fluid, then we understand that the shear stress is simply going to be minus mu times velocity gradient at some specific value of r, where r is the radius of the tube. So, with this approach, we did find what is the wall shear stress exerted by the fluid on the walls of the tube, and we also derived what would be the formula for the average velocity. This is axial average velocity, a velocity across an area which is perpendicular to the direction of motion. So, it is the cross sectional area of the tube across which we average the velocity, and we have obtained an average expression for average velocity. This average velocity profile multiplied by the area would give us the volumetric flow rate. Now, that is the well known Hagen-Poiseuille equation. So, there are some few other examples that we have solved in previous classes. The flow along an inclined plate, or the flow along the outer wall of a tube when the flow comes from below, comes to the top of a tube, spills over and starts to fall along the wall, along the side walls, along the outer side walls of the tube. Progressively, what we have seen is that the approach that we have used so far is appropriate for simple systems where the flow is one dimensional, where the flow is laminar, where the flow is steady, and where the geometry is rather straightforward. But the problems should start to creep in when these conditions are not met. So, we have increasingly felt the need to express these or need to formalize our treatment of transport through any system, even at unsteady state cases. In order to do that, one must first start with some of the 2 or 3 basic definitions of how do we define the derivatives of a system. In this class and the next class, I will talk about what's going to be the partial time derivative, the total time derivative, and the substantial time derivative. These are important concepts which must be clarified before we get into the next part, which is the simple continuity equation. The derivation of the continuity equation, I will not talk about the entire derivation in this class. I will tell you the textbook where it's available, and then we will go into the equation of motion, or a special form of equation of motion of a fluid, which is known as the Navier-Stokes equation. Now, once we have the Navier-Stokes equation with us, then we would see that all the problems that we have handled so far can be handled quite easily by choosing the appropriate Navier-Stokes equation for the flow situation. And once that's done, we will solve a few more involved problems and then move into the next chapter. But before we start, the topic of our today's lecture is the equations of change for isothermal systems. Now, when we talk about equations of change, there are certain definitions which needs to be clarified. So, the concepts of different derivatives, okay, you are trying to measure something as a function of time, and depending on where you are, what are you doing, the values of the quantity that you measure as a function of time can greatly vary. So, I will try to give you an example so that you can have a clearer understanding of these different derivatives. Let us see, you pick the busiest intersection of some place in your town where roads have come from all sides at that crossing. Now, you are standing right at the center of this intersection, and you have been told that please count the number of people who are wearing a blue shirt. Okay. So, you are standing at the middle of a crossing and counting people who are wearing blue shirts. You are not moving, you are static at that point, okay, and you are measuring the number of such people as a function of time. So, every second you try to see how many blue shirts you can see, okay, while you are stuck at a position. So, you are at the center of the reference frame, which is static, which does not move, and any quantity that you measure as a function of time is known as the partial time derivative. Let us say this is the C denotes the number of persons who are wearing a blue shirt, variation of that with respect to time when x, y, z are constant. So, your location is constant, x, y, z is constant, you are right at the center of the intersection and measuring what is the value of C. Now, let us say you while standing there for some time, you are definitely bound to get bored. Okay. So, you get bored and you have decided that enough of it, I am not going to be at that intersection for a long time, I need to walk around. I need to walk around a bit around in the area where I am trying to count the number of persons with a blue shirt. So, you start to move around. You have a velocity of your own. Okay. So, you can go in any direction that you want, and this with some velocity. You are still being a very conscious worker, you are still counting the number of persons with the blue shirt. But since you have a velocity of your own, the numbers that you are counting would definitely be different had you been stuck to the place where x, y, z are constant. So, right at the center of the intersection. So, if you measure the number of people while standing at the intersection, and if you measure the number of people while you start to move around with a velocity of your own, these two numbers must be different. So, when you measure the variation of the number of people wearing blue shirt as a function of time while you have a velocity of your own, by definition it is known as the total time derivative, which is denoted by dc dt, and this dc dt is simply expressed in this, where dx dt, dy dt and dz dt are the components of your velocity. So, u being the reference frame, you start to now move around, and when you start to move around, this dx dt, dy dt and dz dt are the components of your velocity, and obviously the velocity of u will have an impact on the numbers that you count, and that is why it is called the total time derivative and expressed as dc dt. The next one is even just an extension of that. How long you can stand? So, you decided to move with the velocity. How long you can move around? At some point of time you get tired, and being a busy intersection, there's a lot of crowd which are going in all possible directions. So, at some point of time you decide that I had enough, I will simply float with the crowd. So, no matter which way the crowd is, the maximum number of people are moving, I will move with them with the velocity, with their average velocity, and at some point at each point of time I will always move with the velocity of the prevailing crowd at that point of time. But you are still counting the number of persons with the blue shirt. So, now you do not have a velocity of your own. Whatever be the local fluid velocity, that is the velocity of the reference frame, and the numbers that you are counting is some sort of a derivative, that dc dt, that time derivative of the number of persons is a derivative where the reference frame moves with the fluid with its average velocity, or that means it can also be said as it's a derivative following the motion. So, this is generally called the substantial time derivative. In essence, it's a derivative following the motion of the fluid, and it's expressed as del c del t plus Vx times del c del x, Vy times del c del y and Vz times del c del z, where Vx, Vy and Vz are the velocities of the fluid at that point, at that instant of time. So, mark the difference between these two. Okay. So, these are velocities of u, that you have decided to move with this velocity, whereas these velocities are that of the fluid surrounding you. So, you let go yourself and float with the fluid, and the numbers that you count are now known as the substantial time derivative or the derivative following the motion. So, the concepts are important in our subsequent development, where we find out what is partial time derivative, where the stationary frame is fixed, the total time derivative where the reference frame has a velocity of its own, and the substantial time derivative where the reference frame has the velocity as that of the fluid. So, with these concepts clearly understood, now we are in a position to derive what is going to be the equation of continuity. An equation of continuity is nothing but a statement of conservation of mass. So, if I define a control volume in space, fixed in space, and allow fluid to come in and go out through all the possible phases, then the rate of mass of fluid coming in minus the rate of mass of fluid that is going out must be equal to the rate of accumulation of mass inside the control volume. So, in minus out must be equal to accumulation, and this is nothing but this statement of conservation of mass, and we are going to derive the equation of continuity for a system with a Cartesian coordinate system, and the dimensions of the volume is simply going to be del x, del y and del z. So it's a box whose dimensions are del x, del y, del z. It's placed in a flow and the liquid is coming in through the x phase, y phase and z phase. Liquid enters the control volume, and through the phase at x plus del x, y plus del y and z plus delta z, the fluid leaves the control volume. And as a result of this, there is going to be some amount of mass accumulation, if possible, within the system. So we are going to write the balance equation for such a system and derive the equation of continuity. So in order to derive the equation of continuity, the way we are going to start it, we define a coordinate system x, y, z, and we have, as I mentioned before, there's a box and this box. So this area is, let's say, delta y from here to here. This is delta x and this is delta z. Okay. So the some amount of mass is coming in here through the x phase and the mass that is going out. So the x phase is defined as this phase which has areas del y, del z. So this is your x phase, and on the other hand, on this side you have the x plus del x phase. Similarly, this phase whose area is del x times del z is known as the y phase, and I have a y plus delta y phase on the other side, and this is my z phase, so which has areas of del y times del x. So we are going to write the amount of mass which comes in through all these phases. So what's the amount of fluid which comes in through the x phase? So rate of mass in through x phase can simply be obtained as Vx evaluated at x multiplied by del y del z. So this has units of meter square, this has units of meter per second. So this becomes meter cube per second. Meter cube per second when multiplied by rho makes it kg per second. So this is the unit of this. So this is kg per meter cube. So essentially the unit here is you are going to get is kg per second. So therefore this quantity gives you the amount of mass, the rate of mass in, time rate of mass in through the x phase. In the rate of mass out through the phase, again I am talking about x phase only, would simply be rho Vx times del y del z, but instead of being evaluated at x, it is going to be evaluated at x plus delta x, which is this phase. So rho Vx, if you just think of rho Vx, it's kg per meter cube and meter per second. So essentially this is kg per meter square per second. So rho Vs is nothing but the mass flux. So this mass flux, since it's kg per meter square per second, so this mass flux when it's multiplied by the area, corresponding area, would give you kg per second, or the rate of mass in coming in to the control volume. As a result of, so you are going to have 3 in terms and the 3 out terms. The in are at x, y and z phase. The out are going to be at x plus del x, y plus del y and at z plus del z phases. As a result of this in and out, you are going to get there would be some amount of accumulation inside the system. So, your governing equation is rate of mass accumulation must be equal to rate of mass in minus rate of mass out. So, if I substitute these two in here and think of what is rate of mass accumulation. Rate of mass in order to have a mass accumulation inside the system, the density of it must change. So, this is del rho del T is the change in density of the fluid contained within the control volume. So, what is del rho del T? Is kg per meter cube per second. So, this must be multiplied with del x, del y, del z to make it kg per second, and therefore, del x, del y, del z times del rho del T would give you the time rate of mass accumulation of inside the control volume. So, the left hand side is going to be equated to the right hand side, and what you get is del x, del y, del z times del rho del T, which is the accumulation term, must be equal to del y del z, then rho v x at x, this is the in term, minus rho v x at x plus del x, this is the out term, plus del x del z rho v y, which is y, that is the in term through phase at y, minus rho v y at y plus del y, this is the out term through the y phase, plus del x del y rho v z at z minus rho v z at z plus delta z. So, this is the in term in through phase z, out through phase z. So, in other words, in difference term, this is essentially what is known as the conservation of mass. So, the obvious next step would be to divide both sides by del x, del y, del z and take in the limit when all del x, del y, del z tends to 0. So, dividing both sides by del x, del y, del z, and in this condition where del x, del y and del z all approach 0, you get the definition of the first derivative, and the expression would simply be equals minus del x of rho v x plus del y of rho v y plus del z of rho v z. Please note that I did not take the rho outside, because I did not yet put the special condition that the flow is incompressible. So, I am allowing the flow to be both either compressible or incompressible. So, that is why my rho stays inside the differentiation sign. Now, this expression can be expressed in a more compact form is minus del rho v, where this is rho is kg per meter cube and meter per second. So, this is essentially kg per meter square per second. So, this is nothing but the mass flux, which is a vector. So, this is the divergence of mass flux vector must be equal to the time rate of change of density inside the control volume. So, that is one way of expressing the equation of continuity or the conservation of mass. Another way, if you can expand the term, that is I started with this to be equal to minus del x of rho v x plus del y of rho v y plus del z of rho v z. So, this was the equation of continuity, which, and then I can express it, I can simply make it as v x times del rho del x plus rho times del Vx del x. Similarly, for this Vy times del rho del y plus del Vy by del y plus Vz times del rho del z plus rho times del Vz del z, simply by expanding the derivatives. Now, what I am going to do is I am going to bring this term and this term on the left hand side. So, if I bring these terms on the left hand side, it would simply be del rho del t plus Vx del rho del x plus Vy del rho del z plus Vz is simply going to be equal to minus rho del Vx del x plus del Vy del y plus del Vz del z. If you look at the left hand side carefully, it is nothing but what we have written as the expression for the substantial time derivative, del c del t plus Vx del c del x plus Vy del c del y plus Vz del c del z. Simply replace c by rho and what you get is this expression. Okay, so the entire left hand side can be expressed as del t is equal to minus rho. This is another form of equation of continuity where the rho is expressed in substantial derivative form. So, the two common forms that you would get for the case of equation of continuity, one is del rho del t, which is partial time derivative in which is equal to the divergence of the mass flux vector, and the other one is del rho del t, or the substantial derivative of density is equal to minus rho times del v. So, these two together are known as the continuity equation. So, this continuity equation plays a very important role in fluid mechanics, in transport phenomena, because it tells you about it is nothing but a statement of the conservation of mass. So, rate of mass coming in minus rate of mass going out must be equal to the rate of mass being accumulated inside the control volume. And so, I have shown you two different forms for the equation of continuity, and the two different forms can be expressed either in partial derivative form or in substantial derivative form. But there is a special form of equation of continuity with which we are mostly concerned with, which are more common. They are known as the equation of continuity for an incompressible fluid. An incompressible fluid is the one in which the rho, the density, remains constant. It's not a function of x. It's not a function of x, y, or z. So, if the density is constant, if it's an incompressible fluid, then if you look at this expression, it would simply give you the del v is equal to 0, or in other words del Vx del x plus del Vy del y plus del Vz del z to be equal to 0. So, this is the form of incompressible the continuity equation for incompressible fluid, which is rho to be a constant. So, these two equations are equivalent. This equation is a special form of equation of continuity when there is when you do not have any variation of rho with any of the independent variables present in the system. So, we have done the equation of continuity. In the coming class, we are going to do the equation of motion, and once you have the equation of continuity and equation of motion clear in your mind, then you would be able to solve almost any problem of momentum transfer. At least you will be able to formulate the problem. Whether or not an analytic solution is possible, that we have to see on a case by case basis. For each case it may not be possible to obtain an analytic solution, and we may have to resort to other techniques including numerical techniques. But this would give you the tool at least to get the governing equation correct. And the expression for continuity equation which I have shown you is basically for Cartesian coordinate systems. You have similar such relations of equation of continuity for cylindrical systems and for spherical systems. So if you look at any textbook, you would see the expression for equation of continuity in all three possible coordinate systems. Okay, and this part what I am teaching you right now is clearly mentioned in Bird, Stewart and Lightfoot. So the book that I have followed for this part is from Bird, Stewart, Lightfoot's book. Lightfoot's books on transport phenomena. So the equation of continuity in Cartesian coordinate as well as in cylindrical coordinate and in spherical coordinate, they all are provided in this text, and whichever be your system, whatever be your system, depending on that you choose the appropriate expression for the equation of continuity. So next class we will get into the equation of motion.